Just recall that in the first part of this lecture we saw the definition of convergence in R3, and we defined open sets, closed sets, and then we defined bounded sets and so on. Okay, so that was kind of the preparation which we are going to require. So now let us move on and we start discussing about functions of. I have written here several, but we are going to restrict ourselves to 2 and 3 variables. Okay, so I mean, as the name suggests, it's just so what we have, a function, let us call it f, of 2 or 3 variables is a function whose domain is some subset of R2 if I am talking about function of 2 variable, or it will be a domain sitting inside R3 when I am talking about functions of 3 variables. So basically the function depends on 2 or 3 variables, okay, and it takes values in R. Okay, so right now I am just going to take domains in R2 or in R3, okay, but the values of the functions are going to be real numbers. Okay, at some point we will also start talking about functions which are taking value in R2 or in R3. Okay, that will also come, but right now we just try to we begin with the study of functions from R2 to R or R3 to R. Okay, they need not be, these domains need not be the full sets, full spaces R2 or R3. They can be some proper subsets also. Okay, so I mean, such a function is called function of 2 or 3 variable. Okay, and the range is, this is the set that you collect all the values this function take when x comma y comma z varies. I mean, this actually should be the domain. Okay, if the domain is whole of R3, then this is the range, otherwise you just put here D. Okay, because outside the domain of function may not, I mean, it's not defined. Okay, so similarly you put the definition for 2 variables and so on. Okay, so for example, I mean, look at this function. Now this function, we just saw it without calling it a function of 3 variables. So x, which is x comma y comma z, going to the modulus, correct? So this is a function. Basically what it does, it assigns x to a number which is given by this modulus. So this is an example of a function of 3 variables, and here domain, this thing is defined for whole of R3, so domain is full space. Okay, and for example, you can take this function. Okay, it depends on z, x and y in this fashion. Okay, so this is going to be a real number, but this x square plus y square in the denominator, if it is 0, then there is a problem, so you exclude that point, isn't it? So when somebody writes a function, you have to understand its domain. If it is not written explicitly, you should understand that wherever it is well defined, only those points you are talking about. Okay, so and one more function I have given here. Now you see that the square root here, if this guy, the y plus 1 is not bigger than equal to 0, then this is not going to give you a real number. Okay, so for this reason you have to assume that y plus 1 is bigger than equal to 0, because you want your function to land in real numbers. Okay, so basically these are like the simple things which you have to keep in mind. Okay, now once I have a function, I want to study its properties, so I will try to look at its graph. Okay, and there are going to be many ways to study functions, so we will slowly introduce new notions. So graph, as you are aware from the calculus 1 course, what is the graph of function from R to R? You get a curve, correct? So similarly here, what you do, you take the function which is of 2 variables, let's say domain is D. Okay, so its value is a real number. Okay, so the graph of f is going to be a subset of R3. So the first 2 coordinates are the coordinates from the domain, and the third coordinate is the value. Okay, so look at this picture. Okay, but there is a small problem in this picture. You see that here I have written D, which is the domain, but it is written x comma y comma 0. Okay, this is a subset in R3, but this is written because the picture which we have here, it's a picture in R3. So in R3, if I write D just with 2 coordinates, that doesn't make sense. Okay, so technically this D is just a subset of R2, but just to describe it pictorially, we have to put as a subset, put it as a subset of R3. So that is why you have put this. So D is, you know, in the x comma y plane. Okay, xy plane. Okay, so that is the third coordinate is 0. Okay, so what is happening, that you take any point, so the function is going to send it to some number which is recorded on this along the z axis, and then you basically take. So what you get some structure in R3. Okay, some geometric structure in R3, and often it will be written as S or GF. Okay, so now in order to study the function, you know, we will try to understand this thing, the graph. Okay, and there are going to be many, as I said, many ways, because now we are talking about things which are sitting in R3. Okay, so there will be tools to study this. So we will basically, what we will do is we will slowly, as I said, define things. Okay, so for example, let us look at this particular example. Okay, I have this function which is the square root of this 9 minus x square minus y square. Okay, so the first thing you need to make sure that this guy inside the square root is bigger than equal to 0, because you are taking the square root. Okay, so that will tell you that you are looking at I mean, this is, I mean, so easy that you already know about such things. But what I'm trying to just explain to you, that you have to be careful. You know, you should not just say that the domain is everything, and you know, so this you have to make sure this. Okay, so what is it going to give you? The graph is going to look like this upper hemisphere, isn't it? Because I am talking about the plus sign with the square root. Okay, so the graph of f is the upper hemisphere in R3. So here domain is all the points which satisfy this. Okay, so this is going to be a disk of radius 3 in R2. So you see that you know, these points are properly marked, 3 0 0 and then 0 3 0, correct? So this is going to, if you just look at the first two coordinates, this is going to give you a disk, and the height, you know, is, so what I have, this looks like the upper part of the sphere, which is called the upper hemisphere. Okay, and okay, this is something very interesting here, and it's left as an exercise. So this is only like half part of the sphere. Okay, can I express the whole sphere as a graph of a function of two variables? Okay, so this is the question. I am able to write the upper half part of the sphere as the graph of a function of two variables. Okay, can I do the same when if I consider the sphere? So question is, can the sphere be written as the graph of a function of two variables? Think about it. What will happen when I also want to include this? Is something going wrong here in terms of the definition of function? Okay, so think about it. All right, and now what we will do is, you see this thing is sitting in R3. What we will do is, we will you know, cut slices through this. Okay, and that gives rise to the notion of label curves. Okay, this is a tool to study higher dimensional, or like things which are sitting in 3 dimensions. Okay, so the label curves of a function. Okay, so you take a function of two variables. Okay, and this, as I said, the label curves is a method to understand the graph. Okay, and of course when I say graph, you mean you are trying to understand the function. Okay, so what you do is, you take a real number k, you already have this function of two variables, so you look at all the values of f, okay, which are equal to k. So what you are doing, basically you are looking at all the points x comma y in the domain, such that the value of f at those points is constant. Okay, and then you collect all these points. So this is called a label curve. Okay, so look at this. In other words, label curve is the set of all points in the domain of f at which f takes a constant value k. Okay, so if you change k, the curve will also change. Okay, let us look at this example, the example which we gave here. Okay, so you see fx comma y is varying from 0 to 3. Okay, so this k, if I take outside this, it doesn't make any sense, because you know, there's going to be no point which is mapped to that k. So when I say this k, even though you started the definition with k in R, but all you need, this k should come from the range, because finally I am talking about the value of f equal to k. So if this k is not in the range, it is going to be trivial situation. Okay, so those are kind of excluded. So you take any k. So for example, I have taken k equal to 0. Now k equal to 0 here. Okay, so which point is mapped? So the label curve corresponding to k equal to 0 is just the point 0, 0. Okay, and if I take k equal to 3, now what are the points which are going to be map to 3? Again, it's just going to be origin, isn't it? Okay, and if I take something in between, you will see that you are going to get the circles, correct? Because these circles will have the fixed x square plus y square, and then 9 minus that number is going to give you a circle of radius something here, correct? So I mean, all these circles for a corresponding value of k, if you lift them, they are going to sit on this. Okay, so you know what basically is happening, that this equation is going to give you a curve on this 3-dimensional body. Okay, or the surface, if you call it. Okay, so this whole thing is made of these guys. So if you study each of them, you understand the whole graph. Okay, so that is the whole idea. So these things, the label curves are subsets of the I mean, this is the collection of points at which the function takes a constant value, but if you lift them up, they are going to sit as curves on the surface. Okay, so this is how these label curves are defined. Now the corresponding notion can be defined for the functions of 3 variables as well. Okay, but now you will immediately notice when I go to next dimension, so when you have got 3 variables and functions depend on 3 variables, the graph is going to be something in a 4-dimensional space, correct? Because I will have x, y, z, and then the value of f, isn't it? So now that's too much, because R4 we can't really draw, or we can't really visualize it, so this the corresponding notion here is going to be called as label surfaces. Okay, so graph, we will not try to draw, rather we will try to understand what are the label surfaces in the case of functions of 3 variables. Okay, so as in the previous case, label surfaces are just you look at where the function takes the constant value. Okay, and again this k, even though I have written in R, but this should be just varying over the range. Okay, so just collect all the points in the domain at which the function takes the value k, and then you get the label curve, and this k will be called the height. I have written in the previous slide also that k is called the height of the curve. Okay, or the label curve. So at height k, you look at the label curves, and when you are talking about functions of 3 variables, they are not called curves because they are the surfaces. Okay, all right. So label curves in R2 and label curves in the case of functions of 3 variables. Okay, and for example, look at this simple example. Consider this function. Okay, so it's a function which depends on x, y, and z, and what it is, it is x square plus y square plus z square. So you know that this is a point on a sphere, correct? If I take x square plus y square plus z square equal to some k, so this is going to be a point on a sphere of radius square root of k, isn't it? So now as you know that the graph of this will be something in R4. Okay, and so let us try to just see. Okay, I have a picture here from the book. So x square, so several values are there. So x square plus y square plus z square equals to 1. Okay, so this is what, this is a sphere of radius 1. So the label surface at the height, okay, here you should think of k. So k is equal to 1. Okay, so at the height k equal to 1 is a 3-dimensional thing, correct? Because x square plus y square plus z square is a sphere in R3, so it's something in R3. And if I go to next value, okay, so here k is 4. Okay, because you have to take a square root, so that is why so the next value here, I mean, you could have taken 2, you could have taken 3, and so on. So you will get a corresponding sphere. So the whole point I am trying to make here, that the level surfaces, okay, they are going to be sitting in R3, okay, because it's an equation in x comma y comma z, okay, 3 variables, okay. So this is going to be a geometric object in R3, and you know, for each value of k you have this 3-dimensional situations. So if you want to study the graph, you know, at every point you will see that there is going to be a stack of 3-dimensional things, okay. So that is how the 4 dimension will come up, okay, but we won't be able to, you know, go into that. So in order to study functions of 2 variables, often we will see that you need to study the level curves, and to study functions of 3 variables we will go to the level surfaces, okay. All right. So okay, now I define the concept of limit, okay. Just briefly recall that for vector valued functions, recently we defined the limit t goes to a of rt. So here this t was just a parameter varying over the real line, okay. And so in order to have this concept, what we need points which are very close to a, the point under consideration, correct. If we don't have points close to a in the domain, then you know this doesn't make sense, because what we are saying that as t comes closer to a, then how does this function change, okay. That is the whole point. And so for this we always need that, you know, the points near a should be part of your domain, okay. So this is something which we will have to make sure. And when we try to develop the idea of limit for functions of 2 or 3 variables, the same idea is required, correct. The requirements are the same in a way. So we will make sure that your domain contains points which are close to the given point, okay. But here you see, I will again take a small so let's say that I have this domain in R2, okay, and I am interested, let's say I am interested at things converging to the center, okay. So here, you know, when I say the points close to, in the case of real line, there are only 2 possibilities. Either you can approach this point from left, or you can approach from this point from right, okay. But here now, when I am sitting in R2, a point can be approached from, you know, all possible directions, correct. So what I have to make sure that around this point I have all these points in my domain, okay. Otherwise it just doesn't make sense, okay. So this is something we have to make sure, and we will do that, okay. And you will see that, you know, the idea of open sets and closed sets will come, okay. Similarly, I mean, this is just the example for 2 variables, same idea for 3 variables, all right, okay. So limit of functions. So let us take D, a domain in R2, okay, because I started with function of 2 variables. So f is a function of 2 variables, that means this D is a domain in R2, okay, and I take a point in R2. So we have to assume this, you know, we have to assume that this D contains points that are arbitrarily close to the point of interest, okay. So this is an assumption, otherwise, you know, the limit it doesn't really it doesn't make sense, correct. So we say that the limit of f of x comma y is L as this x comma y approaches this given point, okay. In notation we will write it like this, that limit of this x comma y goes to a comma b of f of x comma y is equal to L, okay. This is standard notation. If what happens, if this happens, that for every epsilon positive, if we can find a delta positive such that this happens, okay. So what is happening here, that f of x comma y gets closer to L, okay. So because I started with an epsilon, and for this epsilon what is happening, that this in the delta neighborhood, okay. So this guy is called the you know, all the points which are delta close to the point a comma b, okay. So what you are going to get, you are going to get something like this picture, okay. So because x comma y, so imagine that this is the point a comma b, and then the radius will be delta. So you are basically talking about a small disk, but you see here I have said 0 is strictly less than this. So that means this point a comma b need not be part of your domain, because I am not talking about f of a comma b, I am talking about around this point my function is defined. So this point, the point a comma b need not be part of your domain, and you need to verify this for all points in a small neighborhood. Okay, so basically what you need to do is you take a point here and fix any epsilon positive. This can be very small number and this has to be very small number. So what we are trying to do is we are saying that if I can find a number L, so that this f of x comma y, in the range of f, this number is within L minus epsilon to L plus epsilon. Okay, for all the points in a small delta neighborhood of the point. Okay, so if I start with epsilon equal to 1 over 100, I will find some delta such that this happens. Okay, if I change my epsilon, then this delta may also change. Okay, and you also notice that once this thing holds for a given delta, then the same thing will also hold for the smaller delta, correct? Because that will be a subset of this d delta. Okay, so this d delta here is nothing but this disk with possibly the center removed. Okay, so this limit is basically that as I approach the point a comma b, the value is the value of function is approaching L. Okay, and here this approach here is happening in R2, so that is why that you have to approach this from all possible directions. This is very important. I am not approaching this point a comma b, let's say along the x-axis or along the y-axis. Okay, I am approaching it through a small disk around it. So that means I am considering all possible points around it. This is very crucial in the limit. Okay, if I just approach it, because I can approach it along a line which is parallel to, let's say, y-axis, then I can start here and then go here. This is one approach, and I could have done I could have done this way also. So there are infinitely many directions here, but we have to take them simultaneously. Okay, we cannot just say that okay, I go through this path and then I am approaching a comma b, and if I find the values are approaching L, then I call that limit. No, that is not the case. Okay, the definition of limit says that you approach this point from all possible directions simultaneously. Okay, so yeah, I think I have written these things in the remark. So we have assumed that D contains points which are close to a comma b. This is a requirement to make sense of the concept of limit, and this point need not be in the domain. Okay, right now, and note that in definition of limit, we are required to take x comma y in a small neighborhood. So neighborhood is that d delta, correct, of points a b, and because we can approach in R2 a point through many directions, and you need to take them. I mean, you need to basically approach the point from all possible direction. Okay, so this is exactly the same thing, and then this is simultaneously, as I said. And this thing that approaching the point from some particular or a specified direction, we will discuss some examples about that, but that will be a different thing. And as I said, this is a local property. Finding the limit is a local property, because what you are doing is, if I am interested in the limit of the function at this point, then I am just worried about the function near this point. Okay, so this is what the meaning of local, that this property of limit is local, and it doesn't depend on the points which are sitting away from the point a comma b. So this basically all you need to worry about the points which are close to a comma b. Okay, and as in the case of limits for real numbers or functions of real numbers, here also the limit is unique, which you can verify. So what I am saying here, that suppose the limit exists, okay, and it is given by two numbers. Okay, suppose this limit is also L1 and also L2, then you must have that L1 is same as L2. You cannot have two different limits of the function when the point is fixed. Okay, and how do you prove? This is precisely the same proof. You look at the difference, so that this difference is 0, correct? So when you want to show that some positive number is 0, I should not say positive number is 0, I should say some number is 0, what you do? You show that the modulus of that is arbitrary small, isn't it? So you do the same thing. You look at the difference, take the modulus, and since the limit involves the difference, you just add and subtract f, and then use the triangle inequality, Now this triangle inequality is the triangle inequality for numbers, correct? Because L1, f of x comma y, all these guys are real numbers. So you have this. Now I know that this guy, because I am assuming that the limit is L1, this guy is becoming very small. Similarly, this guy is also going to become very small. So the difference will become very small, isn't it? So you see that this is going to be less than 2 epsilon, because one epsilon is this, another epsilon is this. So for any epsilon I can do this. So there's only one possibility, that L1 is equal to L2. Okay, so let us look at some examples also. Okay, so simple example, let us say that f is defined by this x comma y is being sent to x times y. Okay, so x times y is a number. Now you see that x times y makes sense for all x and all y's, isn't it? So the domain is whole R2, and if I am saying that what is the limit x comma y going to 0 0, does it exist? If it exists, then what is it? Okay, so basically there are two questions, isn't it? So you can see that when x and y both are approaching 0, okay, the product is also going to approach 0. Okay, so our guess is like this should be 0, and how do you prove it? You just write it down. So first you have to make a guess, and then you try to prove it. Okay, so x times by minus 0 I need to compute, correct? Because L is 0 here, but you don't want to write that 0 again and again. So x mod of xy is less than or equal to this number. You know this, correct? Just to the a minus b square, okay, whole square. And what I want, just look at the definition. So apply the first principle. You want to find for a given epsilon a delta. Okay, now here the point is 0 0. So what is this? This is just going to be mod of x comma y is x square plus y square in the square root. So you want to say that whenever x square plus y square is less than delta and square, then I should have that f of x comma y less than epsilon. Okay, so let us just write. So you started with some epsilon and you want to find this delta. Okay, so I want to make sure that this implies that f of x comma y is less than. Now you see this inequality here. Okay, this is nothing but modulus x comma y square, which I want to take as less than delta. Okay, so if this is less than delta, so what I will get, this is less than delta square by 2, and I want to make this is less than epsilon. So basically whatever number you are getting here, you just write in terms of epsilon. So if I take delta equal to square root of epsilon, then I get that mod of x comma y, which is less than this number, and which is less than delta square by 2, and then if I write delta is equal to square root of epsilon, so I get this epsilon by 2, which is less than epsilon. Okay, so you have to practice this. You take some elementary functions and try to find that which delta is going to work. Okay, so but a lot of guesswork is going to be needed here, because this was a simple situation. But if I change a function a little bit, then you have to understand that first that what should be the limit, that you have to think, and then try to prove it. Okay, I have written another example here, that x comma y is now going to x by divided by x square plus y square. Okay, so as earlier, x square plus y square doesn't make sense when both of them are 0, so you have to exclude the point 0 0. Okay, so this is a situation when the point at which you want to find the limit is not part of the domain. Okay, but that's not required. All is required that you should have points near this in the domain, but this has all the points, only the one point is missing. Okay, now you see that. Okay, let us try to guess what should happen. So x and y both are going to 0, then the numerator will go to 0, and similarly denominator will also go to 0. Okay, and this is not a good situation, because this can lead to 0 by 0 type of situation. Okay, so then we have to be more careful here. Okay, so whenever such a situation arises, what happens, we have to take some particular points and try to see how the function is behaving. Okay, so in particular you fix x equal to something and y equal to something and try to see how the function is behaving, and we know that if limit exists, then it has to be unique. So all that combinedly you have to use. So for example, I am going to put one of the coordinate to be 0. Okay, so let us do that. So if I evaluate the function along the x-axis, okay, both I cannot take 0, but one I can take 0. So what I am going to get, x by will be 0, okay, and in the denominator x square will be there, which is non-zero, so it makes sense. So fxy is 0. So now I can take this x very close to 0. So that means I can take the point x comma 0 very close to 0 0. Okay, so if this function is having limit at 0 0, it has to be 0, because it cannot be any other value, isn't it? Because limit has to be unique. I can see that along this the function is throughout 0, so the limit has to be 0, and similarly along the y-axis also this is happening, isn't it? But just one small change in our point of view. If I, instead of x comma 0, I take x comma x, okay, so x by will become x square. In the denominator, x square plus y square will become 2x square. Since x is non-zero, I can cancel x square and I get half. Now you see, if I am approaching along the axis, I am getting 0. If I am approaching along this line, I am getting half, but 0 is not equal to half, correct? So this suggests that the limit should be half, this suggests that the limit should be 0, okay, but this cannot happen because limit has to be unique. So immediately you conclude that this limit does not exist, okay. So these are the ways which you have to adapt to and utilize, and use your intuition that which particular path you should choose, and to so that you get some insight into it, okay. So all that will come with trial and error. There is no fixed rule, and one has to keep doing it, okay. So solve a lot of problems about finding limits of two variables, and you see that there is a difference when we dealt with functions of r, and now when we are dealing with the function of two variables, okay, because here there are so many directions which you have to take care of simultaneously, okay. So I stop here, and then the next lecture we will start talking about continuous functions and so on, okay. So